Hello and welcome to another C tutorial video. In this one we will see the difference between traditional recursive and tail recursive implementations of the same problem. So as for the example, I've chosen the Fibonacci number, which is defined as follows. For f0 it's 0, for f1 and 2 it's 1, and for fn it's fn minus 1 plus fn minus 2. So, and here I have some examples, some results printed, which we will use to check against. So at first I will implement the traditional recursive implementation. Traditional recursive Fibonacci. Here we get our n, and then we have like the condition to exit, and that would be just n if it's either 1 or 2, we will return 1, and for any other case we will make a recursive call again the same function with n minus 1 plus n minus 2. So in few lines we have now implemented the Fibonacci number. We can test now for 10 if it's implemented correctly. The traditional one is straightforward. It's the mathematical definition we implemented, and the tail recursive is a bit more tricky, but however that's also not rocket science. We see now our result, which is 55, and for f10 that's correct. Maybe we could also say result 10, result 11, with the underscore, it's better readable. Okay, we have here now 10 and here 11. That's not required anymore. We will now execute our program to see whether it works. And in our case, yes, it works fine. We have 55 and 89 as a result. This one is the traditional recursive one. We have here recursive calls with just changing the argument, decreasing the parameter by 1 and 2. And as we reach like this value here, we return 1, and the add operation takes place as the final step. So all the calls are done and evaluated, and afterwards when we have like the result like these ones, then they're added or the sum is built. So we have here lots of calls, lots of stack frames which need to keep track of the state of the variables. Hence this is not so optimal. Another possibility is to solve this problem iteratively, so just by using a for loop. That would also be possible, and we could then just implement it in a linear fashion. So if it would be like performant compared to this implementation. However, we will, in order to see the difference between traditional recursive and tail recursive, we will implement now the other variation of it via tail recursion. So for doing that, we define another function which is called tail recursive Fibonacci, again with the n. Now we need a helper function which we can denote as helper. Here we need like several parameters. First of all, we need like the counting, as for counting the steps, so we know how when we finish we need to have a counting variable. Then we need to keep track of our last steps, so we will call that I, and finally we have like accumulation or something like the result, yes, the result, which will be the final result we return. And the condition for this is now like if we reach n smaller 3, then we return our result, and for any other case we make a recursive call with -n, so that we increase it beforehand, or better like this. Afterwards we write the result at this position, and now the addition takes place. We compute result plus I. Now we just need to call this function within here. We pass the n. Now we need to pass like I, which is 1, and the result is also 1. So this just reflects these two cases here for f1 and f2. We just pass them, and as you can see, we just compute then this 1 plus 1. It gets 0 in the next 2 in the next step, and then we pass it to this position and add the result from before to this one, and so we build up our Fibonacci number. Now we can just give it a try if it works. I hope so. We just copy this, and we, instead of this, we just use the tail recursive one. And we can again print them, and let's see if it works. So as you can see, we have here 55 and 89. So we have seen here two variations of the same problem, or of, yes, of the same problem. And this one, the tail recursive one, here is different from the traditional recursive in terms that it just can be thought of a iterative version of the Fibonacci number, because we step through, we make recursive calls, and the final call to this function where this condition is met, the result is gained or just returned. So we step through, and for the final call where this condition meets, we just return the result. However, in the traditional recursive one, we step through, we reach this condition where we return 1. However, we have this add operation here, and that's the operation which takes place as the final step. So building all these ones and these additions, and afterwards, if when all calls are evaluated, then the sum is computed. And you can think that lots of stack frames needs to be generated in order to persist the state of the variables. And we can also, I think we can also like visualize this by, let's say, print stars. And we have here in number the stars which are printed, and now we just print this number of stars plus f. We print the stars, and at the end we have a line break. So let's call this function between the condition and the recursive call. Let's say we print it n times, and here we do the same, print it n times. So let's see what we get as we print this. However, so that we have just less stars, let's say we can just comment this out, and here we can say traditional recursive call, and we do it for n6. We print this one, and here we see like at first we have 6 stars, 5 stars, 4 stars, 3 stars, 3 stars, 4 stars, and 3 stars. So if we would like increase this, you see that we have the same number of stars several times in our iterations. Like here 6 times, just once. However, we have then 5, 4, again 4, no, just how many is this? 7, yes, 7, 6, 5, 5, 4, 4, several times 3 stars, you can see, right? So we reiterate certain steps, whereas in the tail recursive one, it's much easier, and it's just once. We will see that now. Let's comment this out. As you can see, we have here like it's decreasing just by 1, and when we reach like the final condition, then we return the result, and that's it. No reiteration. So that is why the tail recursive implementation is most of the time more efficient. More efficient because here the complexity rises and it's exponential, whereas here it's just linear, a linear complexity. However, in terms of readability and understandability, you can argue that the traditional recursive one can be read easier and can be understood in an easier way, whereas the tail recursive requires like more thinking, requires more intermediate steps where we just compute sum up. So we take, or we build the solution as we reach the end of our iteration in the tail recursive one. So we keep track, we build up, and when we reach the final condition, we just return the final result. That's it for tail recursive. So I hope by this implementation you will get an idea how different traditional and tail recursive implementations are, and consider in your implementations whether you want to stick with the traditional one or want to optimize it and just reduce complexity to be more performant. It's up to you. I hope you enjoyed this video, and if you like this video, please leave a thumbs up and I hope to see you the next time.